Hello everyone, my name is Puya Pakshad and I'm a PhD candidate in the Department of Information Technology and Management at the Illinois Institute of Technology in Chicago, United States. It's my pleasure to present our research paper titled IEPIS and Intelligent Endpoint Protection and Insight Systems. This work is a collaboration between the Illinois Tech University from United States, Birla Institute of Technology from India, and the British International School of Chicago. And I would like to thank you, my co-authors, Professor Rahul Patel, Batra, Das, and Alapangosh for their contributions. Let me start with the outline for the first part of the talk. So I will begin with the introduction section, includes the background, motivation, and the contribution of the proposed frameworks. Then I will talk about the proposed architecture and its components, which is the IEPIS. Then I will present the research questions of the IEPIS paper. Then in the section 4, we talked about the experimental results and our findings through our experimental results that have conducted. Then we answered the research questions completely. And finally, we talk about the conclusions and the future works. So let me start with the background. So as you know, these days, enterprise endpoint devices like servers, laptops, mobile devices, all are key targets for the cyber attacks or the adversaries for malicious activities. There are lots of different security tools to trying to prevent from these attacks or detect the malwares, vulnerabilities, or any other malicious activities or abnormal behaviors in the endpoint protection tools. So the traditional endpoint security tools, they mostly based on the static rules, or they are mostly based on the signature-based detection tools. However, they are successful to detect the malwares or the bugs, vulnerabilities, or any other type of the bugs, but they mostly fail to detect the unseen attacks, and they require constant signature updates from the vendors. That's their limitations. So these models actually fail to adapt to real-time threats and also configuration-based anomalies. Means if there are some configuration anomalies in the system, so the attackers can try to gather the information and find them, and then trying to manipulate the codes of the system based on the configuration anomalies exist in the endpoints. So as you know, there are several examples in real world as the incidents that they show this hidden risk, this hidden risk in that they can make a problem, they can make a serious issues. So as an example, the Stanex and the Solars attacks, they are the good examples. So because however, they prove that even they are the trusted systems, they can be compromised as well. And this shows a major gap. So the gap is the static policies cannot adapt to modern context-aware threats. So that makes our motivation. So you know that we notice that existing endpoint tools often lack real-time adaptability, depend on manual setup, and fail to interpret context. And attackers can exploit the misconfigurations rather than direct code vulnerabilities. It means if they want to, instead of just trying to find the bugs or the malwares inside the system, trying to execute the malwares, they can also exploit the misconfigurations that they are like a by default configurations of the systems. So that insight motivated us to design a framework that learn continuously from telemetry and adjust the configurations automatically. So this idea became the IEPIS, our hybrid machine learning and LLM-based system capable to continuously intelligent risk evaluations. So for the contribution, I can explain that our main contribution are in these 4 items. First, we designed a modular adaptive framework for continuous endpoint assessment. Second, we combined TabNet and random forest algorithms with LLM-based telemetry filtering for interpretable context-aware learning. Third, IEPIS is the vendor agnostic and auditable, suitable for compliance security standards like NIST or ISO. And four, on 10,000 endpoint, different endpoints as part of our experimental result, IEPIS achieved the accuracy like 90%, reduced the mean time to detect by 84%, and cut false positive something like from 30% to around almost 8%. So the next part I will talk about the IEPIS. This is the architecture, the purpose architecture of the IPIS has the input parts come to the main components, includes four main purpose architecture includes the four components: data collection, feature engineering, risk analysis, and the dynamic controls. And there are two different feedback loops comes from one from the fourth component to the first component, and the next one comes back from third component to the second component, and the security report would be our output of the proposed frameworks. If I want to explain better than, so IEPIS operates as a modular end-to-end protection frameworks. The input is endpoint telemetry include registry files and user behavior. There are main four components: data collection, which is responsible for gathers and validates the endpoint telemetries; feature engineering as a second component, filters and transfers data using LLM-based rules. The third component is risk analysis, which acts like hybrid ML and LLM model perform risk scorings. And dynamic control, the last component, executes remediation and generates the reports like the security alerts. And there are two adaptive feedback loops connects module for continuous learnings. The first component is the data collections, which the input of that is raw telemetry from enterprise endpoints. And so all data are validated, tagged, and transmitted security via TLS 1.3, and the result would be clean, unified telemetry data sets ready for further analysis. The feature engineering components is the module that applies GPT, the LLM, the GPT semantic filtering to extract relevant information. It focuses on 7 core controls: BitLogger, TPM, Smart Screen, FIPS, UAC, autoplay, and password length. These are encoded into structured feature vectors that represent each device's security states. So the output of these parts is the enriched feature vectors with semantic context. The risk analysis module is responsible here for to employs the tabnet to learn feature importance, while random forest algorithms provide stable classifications. The large language model GPT adds context by considering the endpoint role and the security policies. And each device receives a numeric risk score and a category like low, medium, or high risk in security standards. The dynamic control is based on the risk score. The system can take automated action through scripts or APIs, send security alerts to administrators, and generate auditable security reports via our LLM report gens components. And this ensures both fast response and transparent accountability. And let's talk about the feedback loops. IEPIS learns through two adaptive feedback loops. The first one is drift signal loops feedback. Feedback comes from risk analysis to feature engineering whenever telemetry patterns shift. And the post-remediation loop returns from dynamic control component to data collection component to verify that fixed work. These loops makes IEPIS self-improving and resilient. Let me talk about the research question part. So we have two research questions. The first one is, can machine learning methods plus generative AI like LLMs accurately detect configuration-based vulnerabilities and behavioral anomalies? And the second question is, can self-healing mechanisms reduce detection and response time compared with traditional security configuration management tools? So let's start to talk about experimental results and our findings, and then we got back to answer the research questions. The setup parts is in the setup parts we start to examine more than the 10,000 endpoints simulated with IEPIS agents. Operating systems mix with 68% for the Windows, 21% Linux, and 11% for the macOS. And the telemetry included process configuration and user events, and the data securely transmitted via TLS 1.3 in the first component in data collection. And the security labels defined using the standards like CIS and the NIST standards version 853 as the compliance baselines. In the model configuration, we are in the model configuration slide. So we use a hybrid model combining tabnets and random forest algorithms. Tabnets add interpretability, random forest reduce the variance. The dataset was split 70% for training, 50% for validation, and 50% for testing part. With the tenfold cross-validation, we benchmark against a rule-based security configuration management system using the benchmarks precision, recall, F1 score, MTTD, and MTTR, means mean time to detect and mean time to response. IEPIS in the evaluation showed a strong generalization with macro-micro accuracy like 90% and F1 variation less than the 0.4%. And LLM filtering improved precision and recall by reducing noise. And IEPIS outperformed with both SCMs and open source tools like GRR and OS query across all the risk levels. Comparative performance, the figure 2 from the papers showed the comparative performance of the IEPIS and the baseline SCM across three different risk levels like low, medium, high. So here we have this comparison, and it shows that the IEPIS remains balanced in low, medium, and high risk, while SCM drops especially for medium risks. This proves our model detects subtle issues with bias or overfitting. Risk level separability. Here we have the figure 3 of the paper showing the ROC curves aggregated across validation faults, showing balanced discriminations between high, medium, and low risk classes. So the ROC curves show clear separation among risk classes with average accuracy 90%. High accuracy means IEPIS can not only detect malware, but also rank the endpoints by risk level accuracy. So here we have another figure of the paper, like figure 4, which is the normalization confusion matrix on the held out test split, showing proportional prediction for low, medium, and high risks. So means the configuration matrix shows balanced prediction with no bias towards any classes. Minor overlap between medium and neighboring classes is expected because their configurations are similar. Overall, IEPIS achieves consistent, reliable, multi-class classifications. This is one of the tables from the paper. So from an operational perspective, the improvements are significant. Mean time to detect dropped from 7.22 hours to 1.1 hours, and 84% reductions. And mean time to response improved from 15.4 to 9.2 hours, and false positive fell from 12.8 to 7.9%. So this means IEPIS enable faster, more trustworthy detection and response. In practice, these numbers translate to real benefits from security teams, less time spent chasing false alerts, and quicker containment of actual threats. It's a major gain in efficiency and reliability. This table shows a medium risk endpoint evaluated across 7 controls. 5 were mismatched: BitLogger, TPM, Smart Screen, Autoplay, and Password Length, while FIPS and UAC were complaints. These differences highlight the specific configuration gaps IEPIS can detect. Such mismatches increase exposure to attacks. IEPIS detect these policies level violations automatically and translate them into actionables. Uh, it bridges the gap between raw telemetry and strategic security management. Let's answer to the research questions. So the first question, the answer of the first question is yes. IEPIS achieves consistent precision and recall across low-level and high-risk classes. ROC and configuration mark tricks confirm balance class separation with AUC greater than 96% and F1 variation less than 0.45%. And LLM-based feature filtering enhance detection of configuration level risk beyond signature-based SCM. And for the second research questions, the answer is yes. The MTTD improved from almost 7 hours to almost 1 hour, and MTTR reduces from almost 15 hours to almost 9 hours. And the false positive decreased from almost 30% to almost 8%, improving the reliability of automated response. And the projected automation further lowers MTTR to 3.55 hours, confirming IEPIS operational efficiency. As a conclusion, we can say the IEPIS introduces an intelligent endpoint protections and insight systems that combines machine learning with generative AI for adaptive cyber defense. It achieves high detection accuracy, balanced risk classification, and faster response time while maintaining explainability and compliance. And in future work, we plan to extend automation for continuous self-healing and integrate multi-agent reasoning for larger scale enterprise deployments. Thank you everyone that you attend and watching the video of my presentations. We would be happy to take any question if you have. So please feel free to contact us with 2 emails of Professor Patel and me with rpatel137@illinoistech.edu and ppakshat@hawk.illinoistech.edu. Thank you very much.